The boundary line for standard human intervention in the ocean is often defined by the physiology of breathing compressed air. Beyond a certain pressure, the nitrogen in the atmosphere becomes narcotic, and the oxygen becomes toxic. In the murky waters of Hansa Bay off Papua New Guinea, the seabed lies at 213 feet. This depth is a fortress. It effectively seals the bottom from casual access, from recreational diving, and for decades from official recovery. For 80 years, this water column protected a specific debris field from salvage, from looting, and from discovery. At 213 feet, the pressure is roughly 7.5 atmospheres absolute, more than 7 times what a human body feels at the surface. To work here requires more than courage. It requires an engineering solution to the problem of human survival. The object resting in the sediment is a Consolidated B-24D Liberator. Its serial number is 42-41216. The nose art painted on its fuselage read, "Heaven Can Wait." It belonged to the 320th Bombardment Squadron of the 90th Bombardment Group, a unit known visually by a Jolly Roger-style skull emblem painted on the tail fins of their aircraft, often shown with crossed bombs rather than simple crossbones. This group, often referred to as the Jolly Rogers, operated heavy bombers in the aggressive, low-altitude environment of the Pacific Theater. On March 11, 1944, this specific airframe was part of a bombing mission against enemy positions at Borum Airfield and gun emplacements at Awar Point, Hansa Bay. It was a mission meant to smash defenses on the ground, but the aircraft itself became a target. Witnesses flying in formation alongside Heaven Can Wait observed the failure unfold in real time. Japanese ground fire struck the bomber during its run. Fire erupted in the bomb bay, a critical structural junction in the Liberator design. The airframe pitched up violently, an aerodynamic reaction when control cables burn through or the center of gravity shifts rapidly under structural compromise. The bomber banked hard to the left and impacted the surface of the bay. Witnesses flying in formation alongside Heaven Can Wait observed the sequence of failure. Japanese ground fire struck the bomber during its run. Fire erupted in the bomb bay, a critical structural junction in the Liberator design. The airframe pitched up violently. This is a common aerodynamic reaction when control cables burn through or the center of gravity shifts rapidly due to structural compromise. The bomber banked hard to the left and impacted the surface of the bay. Observers reported 1 crew member bailing out with no parachute and 2 others bailing out with parachutes that did not deploy. 11 American airmen were listed as missing in action. The kinetic energy of the impact shattered the airframe, scattering wings, engines, and fuselage sections across the bay floor. Then the silt settled and the site vanished from surface view. For the next 8 decades, the location of Heaven Can Wait remained a coordinate on a missing aircrew report, not a physical destination. The technology to locate a scattered wreck in a featureless bay existed in theory, but the logistics to recover it were prohibitive. Shallow water wrecks are often scavenged or disturbed by storms. Deep water wrecks are preserved by their inaccessibility. This site sat in the dark zone. It was too deep for breath-hold diving and too deep for standard recreational scuba operations, which are commonly kept around 130 feet for safety and simplicity. Yes, trained technical divers can go deeper with mixed gases and longer decompression, but that leap changes everything. Logistics, risk, and the margin for error. The site remained undisturbed because the cost of entry was too high. To reach the crew of Heaven Can Wait, a recovery team would need to bypass the limits of ambient pressure diving. They would need to employ mixed gas supply systems or saturation diving techniques. This requirement elevates a recovery mission from a logistical operation to a life support engineering challenge. DPAA has described this specific project as its deepest underwater recovery mission in service of repatriating missing personnel. Finding the aluminum was only the first gate. The real barrier was the physics of keeping a diver alive long enough to excavate it. The evidence of the 11 men inside the B-24 has been waiting since 1944. The recovery clock did not start until the technology could match the environment. The story of this aircraft is not just about the loss on that day in March. It is about the transition from a missing plane to a forensic crime scene protected by the ocean itself. The debris field contains the answers to what happened to the crew, but the environment demands a price for that information. The question is not where they are, but how to reach them alive. The structural failure of a heavy bomber is a sequence of physics, not fate. The Consolidated B-24 Liberator relies on a high aspect ratio wing, known as the Davis wing, which provides efficiency at cruise but is vulnerable to damage. The design clusters volatile systems, including fuel transfer lines and hydraulic reservoirs directly above the bomb bay. When anti-aircraft shrapnel penetrates this specific volume, the resulting fire is not merely a combustion event. It is a structural attack on the central wing spar. Witnesses on March 11, 1944, observed flames venting from this section, followed by a sudden pitch-up. This maneuver indicates the fire likely severed the control cables to the elevator, or the structural integrity of the wing root failed, shifting the center of lift instantly. When the aircraft hit the surface of Hansa Bay, it did not ditch in a controlled glide. The geometry of the impact suggests a high-velocity collision with the water. Water at impact speeds acts like concrete. The kinetic energy shattered the fuselage, stripping the wings from the center section and tearing the engines from their mounts. The heavy components, such as the Pratt and Whitney radials and the landing gear, sank immediately. The lighter aluminum skin sections drifted in the current before settling. The result was a debris field, not a coherent wreck. Each separated component became a clue, distributed across the bay floor. Once the debris settled, the environment began to process the aluminum. The waters of Papua New Guinea are warm and rich in electrolytes. This creates a chemical reaction known as galvanic corrosion. The aircraft is constructed primarily of aluminum, but it contains steel in the engines, guns, and landing gear. When these dissimilar metals are submerged in salt water, they form a battery. The aluminum acts as an anode and sacrifices its material to the steel cathode. Over 80 years, this process converts strong alloy into a brittle oxide. The structure may look intact to a camera, but it has lost its mechanical resilience. This decay clock runs constantly, weakening the evidence with every passing year. The bay itself adds a layer of concealment. Hansa Bay is fed by river runoff, which deposits layers of silt and mud over the bottom. This sedimentation process buries the wreckage, protecting it from currents but hiding it from sight. The burial creates an anoxic environment, which slows down biological consumption of organic material, potentially preserving human remains. However, it also means the debris is not sitting on top of the sand. It is inside the sediment. A visual search by a diver would reveal nothing but a flat, muddy plain. The evidence is contained within the geological strata of the seafloor, requiring sensors that can see through the earth. There is a final, lethal constraint protecting this site. The aircraft was on an active bombing run when it was lost. It was carrying a payload of high-explosive bombs and thousands of rounds of .50 caliber defensive ammunition. Unexploded ordnance, or UXO, presents a unique hazard in recovery operations. Explosives and fusing components can age in ways no one can reliably predict after decades underwater. A bomb that failed to detonate in 1944 is not safe. It must be treated as live and unpredictable. The recovery team cannot simply dredge the site. They must treat the debris field as a minefield. Every contact with the bottom carries the risk of detonation. The presence of live ordnance dictates the pace of the operation. It forces a strict procedure of mapping and clearing before any excavation can begin. The mud of Hansa Bay hides the identity of the crew, but it also hides the weapons they carried. To find the 11 men, the team must first neutralize the threat that brought the plane down, even 80 years after the mission ended. The search for a submerged aircraft is a geometry problem constrained by the physics of light and sound. In the turbid waters of Hansa Bay, visibility is often limited to a few feet. A diver swimming a search grid would require years to cover the potential impact zone, and the depth limits their bottom time to minutes. To locate the wreckage of the B-24, the team had to remove the human element from the search phase entirely. They relied on a sensor platform that does not breathe and does not require decompression. In October 2017, Project Recover initiated the survey. They defined a search box covering 27 square kilometers based on historical triangulation. To scan this area, they deployed an autonomous underwater vehicle, or AUV. This device is essentially a programmable torpedo. It is not tethered to the surface ship. Engineers program a navigation grid into its onboard computer, and the vehicle executes the mission independently, maintaining a constant altitude above the bay floor. It relies on internal guidance systems to mow the lawn, swimming parallel lines, to ensure 100% overlapping coverage of the seabed. The primary sensor on the AUV is side-scan sonar. This technology does not take photographs. It measures the time it takes for sound pulses to travel to the bottom and return. The sensor emits a fan of acoustic energy perpendicular to the vehicle's path. When the sound hits a hard object like an engine block or a wing spar, it reflects a strong signal back to the receiver. When it hits soft mud, the signal is absorbed or scattered. Crucially, an object protruding from the sediment casts an acoustic shadow, a blank space in the data where the sound did not reach. By analyzing these shadows and highlights, analysts can reconstruct the texture of the seafloor. For 11 days, they ran the grid, parallel lines, full overlap, across the bay. The data revealed a distinct anomaly in the sediment. It was not a geological formation. The acoustic signature showed sharp angles and a distribution consistent with high-energy metal debris. The sonar return indicated a debris field, not a unitary wreck, consistent with a violent impact and breakup on contact with the water. The location was locked, but sonar is not proof of identity. A rock formation can look like a fuselage to an untrained eye. To convert the acoustic contact into a confirmed discovery, the team deployed a remotely operated vehicle, or ROV. Unlike the autonomous drone, the ROV is flown by a pilot on the surface ship via a fiber optic tether. This cable transmits power down to the thrusters and sends high-definition video data back to the control room in real time. The ROV is the eyes of the operation. It can hover, rotate, and illuminate the target with high-intensity LED arrays cutting through the gloom of the deep water. As the ROV descended to 213 feet, the camera picked up the unmistakable evidence of an American heavy bomber. Familiar B-24 geometry emerged in the silt. The long wing planform, the heavy landing gear elements, and engine components where they should not exist on an empty seabed. The survey supported a B-24D identification, but the final validation came from the correlation of the site location with the specific loss records of Heaven Can Wait. The aircraft was found. The mystery of its location was solved. However, an ROV is a confirmation tool, not an excavation system. It can sample, film, and illuminate, but it cannot remove buried sediment at scale or recover fragile biological evidence with human care. The search phase was over. The retrieval phase was still waiting. To bring the men home, someone would have to go down there. The decision to recover the crew of Heaven Can Wait required the United States Navy to authorize a procedure that sits at the edge of human physiological endurance. At that depth, the pressure is roughly 7.5 atmospheres absolute. On standard compressed air, nitrogen narcosis would hit almost immediately, blurring judgment and motor control. More critically, the time required to decompress safely after just 30 minutes of work would be measured in hours. To excavate a bomber from the mud requires weeks of bottom time, not minutes. The only practical way to sustain that kind of work at this depth is saturation diving. In 2023, the Defense POWMIA Accounting Agency partnered with the Navy Experimental Diving Unit to execute this mission. Saturation diving solves the decompression problem by eliminating the cycle of compression and decompression entirely. The divers do not return to surface pressure after every shift. Instead, they live in a pressurized habitat on the deck of the recovery vessel. This chamber is maintained at the same pressure as the worksite on the seafloor. Their bodies become fully saturated with inert gas, typically helium, which replaces nitrogen to prevent narcosis. Once the tissues are saturated, the decompression obligation does not increase, regardless of whether they stay down for a day or month. The commute to work involves transferring from the deck habitat to a diving bell or personnel transfer capsule under pressure. The bell is lowered to the wreck site and the divers swim out to start their shift. They are tethered by an umbilical that supplies breathing gas, hot water for their suits to prevent hypothermia, and communications. For 5 weeks, the team lived at depth, commuting between the pressurized dry chamber and the wet darkness of Hansa Bay. Over that span, the saturation system turned a depth that normally offers minutes into sustained work, delivering 37 diving days and more than 367 hours of bottom time to push the excavation forward. Before a single piece of aluminum was moved, the site had to be documented. The team built a three-dimensional record of the debris field using systematic high-resolution imagery and careful measurement. This digital map preserves context. It allows archaeologists to see where a specific artifact lay relative to the fuselage or the engines, information that is lost the moment an object is lifted. The excavation itself was a delicate removal of sediment. The divers used handheld dredges powered by water flow to vacuum the mud away from the structure. They were looking for anomalies in the clay, the specific shape of a flight boot, the glint of a dog tag, or the density of bone. The visibility was often near zero, forcing them to work by touch. Every bucket of sediment removed was screened and filtered. The goal was not to raise the plane. The goal was to sift the environment for the crew. It was the American government's deepest underwater recovery undertaken to repatriate missing personnel. The physical toll on the divers is significant. At the end of the project, they could not simply step out of the habitat. They had to undergo a slow, controlled decompression lasting several days to allow the inert gas to diffuse out of their tissues without forming lethal bubbles. This is the physiological bill for working at 7 atmospheres. When the diving bell surfaced for the final time, the physical connection to the site was broken. The mud had been cleared and the evidence had been transferred to the surface. The divers had done their job. The engineering phase was over. The mission now shifted from the pressure of the ocean to the sterile environment of the forensic laboratory, where the identity of the material would be tested. The material brought to the surface by the saturation divers is a chaotic aggregate of marine sediment and corruption. It does not look like a crew, it looks like the bottom of a bay. The primary output of the excavation phase is a series of transfer baskets filled with wet sludge. On the deck of the recovery vessel, this material undergoes a rigorous screening process. Technicians wash the sediment through mesh screens of varying gauges, separating the mud from the solid objects. What remains in the sieve is the raw data of the crash site. This includes jagged fragments of aluminum, shattered plexiglass, rounds of .50 caliber ammunition, and personal effects. Among the non-biological artifacts, the team isolates specific items that place the crew at their stations. Life support equipment, such as oxygen regulators and mask fragments, indicates the flight status. Parachute buckles and harness hardware confirm that the men were strapped in at the moment of impact. In some cases, the screening tables reveal the most direct form of identification available in the field, the embossed stainless steel of identification tags. These items provide immediate context, but they are circumstantial. A dog tag proves a specific individual was assigned to the flight, but it does not prove their biological presence in the remains. The forensic standard for accounting for a missing person requires biological certainty. The recovered biological evidence is transported under a strict chain of custody to the Defense WWII Accounting Agency laboratory. Here, the process shifts from marine salvage to forensic anthropology. The first challenge is to separate human osseous material from non-human elements. 80 years of immersion in a marine environment can alter the texture and color of bone, making it difficult to distinguish from wood, coral, or animal remains without microscopic analysis. Once the human material is segregated, the investigation moves to identification. The most durable element of the human body is the tooth. Enamel is the hardest substance in the skeletal system and is highly resistant to degradation even after decades in salt water. The agency utilizes forensic odontology to compare the dental structures found in the wreckage against the dental charts created during the service members' enlistment in the 1940s. A match here is often definitive. The unique geometry of fillings, extractions, and root structures acts as a biological fingerprint that survives where soft tissue does not. When dental evidence is fragmented or unavailable, the laboratory relies on DNA analysis. The environment of Hansa Bay is harsh, but the interior of a bone or a tooth can sometimes preserve the genetic sequence. Scientists extract DNA from the core of the sample and amplify it. Depending on what survives and what family references exist, they may use mitochondrial DNA, Y chromosome DNA, or other genetic methods to build a match. Those sequences are compared against reference samples collected from surviving relatives. The genealogical work done years prior to the recovery now becomes the key to the lock. If the profile from the seabed matches a documented family reference, the identity can be confirmed to a forensic standard. In the case of Heaven Can Wait, the laboratory process yielded results, but not for all 11 men at once. The combination of anthropological analysis, dental comparison, and DNA testing allowed medical examiners to separate commingled remains and make positive identifications for 4 members of the crew. The science transformed a missing manifest into 4 distinct names backed by evidence, while 7 others remain unaccounted for. The recovery phase creates the possibility of an answer. The laboratory phase provides the proof. The unidentified remains buried in the silt of Papua New Guinea have been reclassified. In part, they are no longer only wreckage. 4 are now accounted for, and the work continues for the rest. The classification of missing in action is an administrative state that halts the legal progression of a service member's record. It is a pause button pressed in 1944 that remains engaged until physical evidence forces a release. For 80 years, the crew of the B-24 Heaven Can Wait existed in this bureaucratic limbo. They were listed on manifests and memorial walls, but their status was unresolved. The recovery operation in Hansa Bay was not conducted to mourn them. It was conducted to change their designation. In late 2024 and early 2025, the Defense POWMIA accounting agency began to issue the formal amendments to these records. The agency confirmed the identification of the pilot, First Lieutenant Herbert G. Tennyson. They confirmed the bombardier, Second Lieutenant Thomas V. Kelly, Jr. They accounted for the navigator, Second Lieutenant Donald W. Shepik, and the radio operator, Staff Sergeant Eugene J. Darrigan. These specific identifications validate the entire operational chain, from the initial archival research to the saturation divers sifting through the mud at 213 feet. The recovery of these officers and enlisted men proves that the wreckage field was not just a collection of aluminum, but the final station of the crew. The integrity of these identifications rests on chain of custody, an unbroken record from discovery to final report. In a recovery operation, it starts on the seabed, when a diver places an object into a transfer basket, and continues topside as every item is photographed, tagged, and sealed in tamper-evident containers before leaving the deck. If the documentation lapses at any point in transport or storage, the findings can be challenged. Identity can't rest on probability, it has to rest on verifiable possession. Chain of custody is what turns recovered material into legal certainty for a family. The success of the Heaven Can Wait mission establishes a significant precedent for future deep water recovery operations. It validates a hybrid operational model involving public and private cooperation. The initial localization was achieved by Project Recover, a partnership utilizing academic technology and philanthropic funding to scan vast areas of the ocean floor with autonomous vehicles. This agile approach allowed for a high-risk search without committing government assets to a speculative grid. Once the target was confirmed, the heavy salvage capability of the Navy Experimental Diving Unit was deployed to handle the physiological constraints of the extraction. This division of labor allows for more efficient use of resources, applying the right tool to the specific phase of the problem. The crash site in Hansa Bay remains on the seafloor. The aluminum will keep corroding year by year as salt water does its work. The sediment will eventually reclaim the fuselage entirely, bearing the evidence of the impact. However, the site has been functionally emptied. The objective of the mission was never to salvage the machine. The objective was to extract the crew from the environment that claimed them. With the identifications confirmed, an 80-year open loop begins to close. The operational file for Aircraft 4-4-1216 is no longer a blank space on a report. 4 of the 11 men are no longer missing. 7 still are. The physics of the ocean held them for 8 decades, and the recovery architecture has pulled part of the truth back into the light. The mission is not finished for every family, but the process has proven that the Bay can give answers.